My screen is visible to you?
Yeah. Yes, sir.
Okay. Good morning, everyone. Thank you very much for introducing me and with. So, how much time I am allowed to speak?
Sir, till 11.
1 hour per class, half an hour.
Sir, till 11 o'clock and then half an hour question session. So
Okay.
it's
Okay.
till 11:30.
Okay. Okay.
Thanks.
Actually, I don't know the audience here and what is their understanding and all the things. What I hope is that because this is the last lecture of this program, I think most of the introductory part and
yes, Professor Saroj, I give you a brief outline. Actually, 80% of our faculty in different engineering colleges across India.
Okay. Okay.
And there are few PhD students and very few masters.
Okay. Okay. Okay.
So we can consider dominantly engineering college faculty.
Okay. Thank you. Thank you. Thank you.
In different areas of specialties.
Yes. So
thank you for accepting or may I have requested the last minute.
It's okay. No problem. So anyway, thank you, Professor Ramarao, for giving me opportunities to talk and to meet and discuss some of my research areas with all eminent faculties here. So I'll be discussing something on this granular computing, and basically what will be the flow of this talk will be something like this. It's a concept, actually, granular computing concept. I'll be talking on this concept a little bit. Then I'll just go to the application part of this granular computing in pattern recognition and particularly to remote sensing data analysis. So what we are looking here is that is land cover classifications applications. I'll show you with this granular computing based pattern recognitions. So that is what the flow of this talk today is. Okay. So let me start these things. And I'm presently working in Indian Statistical Institute, a faculty like you. So I hope that today's discussion with you will be a fruitful discussion, and I can justify my presence here in front of you. So actually, I prepared these things in a hurried way. So I'm sorry if there will be some kind of mismatching in the flow or something like that. So, but I'll try my best to maintain that synergy. So this outline will be something like this: the definitions, background, philosophies, advantages, the structures, and computing with granular computing. So that application on pattern recognitions I'll do, and finally I'll make a concluding remarks with the application to land cover classification on remote sensing images. So this concept is something like this. So let me start the whole concept from an example point of view. So let us say I am asking, so I am planning to go to a place, let us say to Delhi tomorrow. So what I'll do is that I'll try to understand the weather conditions, try to understand the situations there in a more or less in a vague way. Okay. So what I'll do is that I'll try to search through Google, or maybe if somebody is there to known to me, and I can ask that person what is the weather condition, this, that, all the things. So that is what we usually do. So we prepare mentally ourselves that wherever I am going, my journey will be comfortable or whatever it is. So let us say I'm asking what is the weather conditions to my friend who is staying in Delhi. So you please try to understand the statement what I am making. I'm just asking what is the weather conditions. So the reply what I'm getting from my friend in the other end is that He's telling it's a little bit cloudy and sometimes it rains and some sun is there. So something like that. So probably I'll be happy with that answer, right? I think if you will be in my position, you will be also happy with that answer. But let us say I'm not happy with that answer. I just wanted to know a little bit more specific about the weather. But my first question was not like that. My first question was, what are the weather conditions? I asked something like this and I got the answers something like this, that it was cloudy. See, there is no quantification of the meaning cloudy. What does it mean? Let us say weather is cloudy, weather is sunny, weather is rainy. What does it mean? It's a kind of conceptual things. It's not the quantifying thing. It doesn't quantify the things. So what I'll do is that maybe in the next questions, I'll ask my friend, okay, it says cloudy or rainy. What is the normal temperature during the daytime or evening or something like that? Probably my friend may say, yeah, it's a bit hot, little bit daytime, and evening time it is a little bit cold. Again, you just try to understand what my question is and what answer I am getting. Still, it is not specific. If I'm happy, it's okay. If I'm not happy, then what I'll do? I'll just ask, no, tell me what is the exact temperature at this point of time. See, I asked 3 different questions. First is that, what is the weather condition? Second question is that, what is the temperature on and around? And third question was the exact temperature. And if I'm getting the questions like initially, what is the condition? Weather condition is sunny and it was little bit hot. And lastly, I'm getting the exact temperature. That is the exact answers. So the point here is that, the message here is that, when my question is not asked specifically, why should I provide the answers specifically? I hope you are understanding the message here. So that means whatever the problem desires for, one should answer that questions accordingly. My problem is not asking me in details. So why shall I scratch my head and spend my money and time to provide the exact answers? So that is the concept of granular computing. Similarly, let us say if I'm trying to look at the world map and try to understand that land covers of this world map. So probably I'll go for, first of all, is that high level informations like continents, countries. Then I may go down little bit provisions, state, areas. Then see, my questions was in a gradation form. So it was not straightforward, directly hitting to that things that what is the land covers here. So I'm not asking that one, or nobody wants to know that one. So from high level information to low level information, this was normally the type of queries we normally make as a human being. Okay, so this is what the concept of granular computing. I'll come to that point a little bit more in a way. So one more example. See, when we all are faculties, right? And we know how to write a technical papers. So when we write a technical papers, we follow certain procedures, right? So we try to understand the things in a high level form, then in the middle level formation, then in the low level formations. High level information, what is that? Let us say title and abstract. Middle level information is chapter, subsections, sub-subsections like that. And what is my low level information? Text. So my way of analyzing the informations, my way of analyzing the problem is in a graded form. It is something to say that if I put these questions in the other way around, let us say one publisher is sending or requesting me to review a paper. So that publisher wants to know the consents from me. Okay, so that publisher will send a email to me. Would you like to review the paper? So this is the questions. So my decisions, what that fellow was asking is that yes or no. Okay, so this is my decision which I am going to provide, and that publisher is expecting from me. But to provide that decisions, should I go word by word to this paper, and after understanding all this whole paper, then should I say that yes or no? Normally we don't do that. So what we do in the first level information itself, we can take the decisions. Let us say I am going to taking I'm taking the decisions yes or no based on the title. So what I'll do, I'll just see the title of the paper. If the title of the paper provides me some kind of information to take a decision, should I review or not, I can provide the decision that time itself. Or otherwise, what should I do? I'll just go to the next level of information. That is abstract. Still, I am unable to provide the decisions. Then what I'll do? I'll go to the next level of informations like chapters and all the things. Still, I am not able to provide the decision. See, why I am not able to provide the decision? Because I am in a confusion. Should I take the decision yes or no? Because my yes and no depends on kind of information that is there in the paper. First thing is that whether it is coming under my scope or not, whether I am able to provide my proper review to that paper or not. So do I work in this particular area or not? So there are so many parameters are there which is forcing me to decide whether I should tell yes or no. So at the end, I can go to that level of text to provide the decision yes or no. Okay. So this kind of gradations normally we follow while providing a decisions. See, decision I am talking in terms of pattern recognition point of view. So whatever decisions you take, whether you take the decisions in the remote sensing domain or medical domain or telecom domain or whatever domain it is. So whenever you are taking decisions, normally we human being take this kind of gradations. First level, second level, third level. First level in the sense high level, next high level, and finally we try to end up with low level information. So at each step, we try to take a decisions. If we are unable to take the decision, then we go to the next level, next level, next level. We can reach to the last level of information, the lowest level of information, maybe to provide the informations. Okay. So similarly, in an image also, I mean, this kind of image can be anything. So let us say my mouse movement is visible to all of you, I believe, because I don't have the marker here. Hello. Hello, can anyone just respond me?
Yes,
My
sir.
mouse movement is
Yes, sir.
my mouse movement is visible, right?
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. So let us say there is a query like you just identify this image. So given this image to us as a human being, we can easily understand. Okay. So this is called a low level information. But if we start breaking that information, and if I only show the either the hair or eyes or nose, and if I ask you, you just recognize the face, you may not be able to recognize the face at that point of time because that information is not sufficient for you to take a decision. So what you do, you keep on increasing your understanding level of the problem just by adding some portions of the image, and finally the moment you come to this stage, you can provide the information. But the problem here is that, as I told you in this example or in the previous example, taking decisions at the high level informations, you don't need to spend much time and money. But taking decisions at the lowest level, you are spending a lot of time. Are you not spending? Because you are coming from high level to lower level. So much of level of information you are coming across to provide the decisions. Okay. So we always try to provide the decision at the highest level itself as a human being, I'm telling. Because this granular computing is one kind of human way of taking decisions. So that is what the concept is. So two things we come across here actually. One is the need for information abstraction, and another is knowledge of abstraction level. One we call it a granule, and another one is called it granularity. See, there are two terms now. I'm just talking about granule. Granule, dictionary meaning of granule, you can understand. Granule, right? Small granules or something like that. So what we do is that we try to break that information to the possible extent. And each of the breaking, each of the some component of the whole big component, we are using a term called granule. Like something like in set theory, subset. So in a paper writing, subsection. So smallest possible component we call it here is a granule. Okay. And the different level of information breaking is called the granularity. So these two terms actually help us to either break or merge the information and provide decisions. Okay. So an umbrella term, actually this granular computing is an umbrella term that covers any theory, methodologies, techniques, tools, and that use granules in the problem solving. So process of performing computation and operations on the granules. Okay. So I'll be a little bit fast because many things I need to cover. So please stop me in between if there is any kind of queries from your end. So there are three basic components we normally realized here. What are these? Granules, granulated views, and hierarchies. Okay. Granule means the smallest information component. That information component in which level you are getting, that is called granulated views and hierarchies. Okay. So granularity in the normal term we use, right? Granularity. That means you break the information to that point where we can provide decisions. Don't break further, because breaking of the information, it requires a lot of effort. Okay. So we don't want to put much effort to provide the same decisions. If you can provide the decision at the first level, okay, without spending much time, I could provide the information. If I'm not getting, then break that. Okay. So the basic structures is internal structure of a granule, collective structure of a granulated view, and overall structure of a family of granulated views. These are all conceptually. Just when I'll talk to the practical point of view, I think things will be much more clear. Okay. So because this granularity we are performing on the information level, we call it as a kind of information granularity. Okay. And this granularity or granular computing, actually, it's not new actually. If anyone is working in the area of soft computing, like fuzzy set theory, rough set theory, from that point of time, from the inception, like let us say I'm talking about fuzzy set theory. So it started in 1965 by Jade. So from that point of time, this granular concept was there, but it was not coined at that time. But the concept we have come from that fuzzy set theory itself. And after the invention of this rough set theory, there is one other set theory that is called rough set theory in 1982. That concept got some kind of boosting. Okay, and that granularity concept slowly coming into the pictures. Now that granularity concept, although we are using, but we never used a term like this, that granularity, a kind of granular informations, breaking the informations. Okay, so this concept is not new, but this usage, the applicability is new. So people are heavily using this kind of concept to take a decisions, particularly in pattern recognition point of view, to provide decisions on the remote sensing data analysis. I'll show you an example on that one and some results also. So you can see from here where from it started. So it started from the fuzzy set theory, and before that it started the interval analysis in mathematical term, if we can remember. So it started from the interval analysis, then fuzzy set, then rough sets. Okay, 1956, 65, and 82. These are the I'm sorry. This is the way these granular concepts came up, and these are the different other domain things which normally works similar to the granular computing, something like that fuzzy set theory, rough set theory, shadow sets, probability granules, set theory, interval analysis, all the things are there which works with the similar kind of principles of granular computing. Okay, so I'm just moving a little bit fast. So the main driving force of granular computing, as I mentioned, is the fuzzy set theory and rough set theory. However, the connections to other fields also is there, and which are something like wavelet transform, neural network. So what they have done is that, I believe you are understanding the meaning of the particular domain like wavelet transform and neural network. So these are also one kind of tools which we can use to take decisions. Okay, so the moment we incorporate the granular concept in that particular things, let us say in wavelet transform, we are incorporating granular concept there. So we can call it as a wavelet granules. Okay. Now let us say there is a term called neural network. Alone neural network cannot take a better decision. So what do? We incorporate some other things, so many things with neural network, like fuzzy set theory, rough set theory, and it becomes a new name, right? Neural network, neurofuzzy, neuro-ROP theory. So like that, if we incorporate granular computing into neural network, so that network becomes granular neural network. So people are also using that one. So there are certain advantages are there, which they are getting if they don't use the granular concept in neural network. Okay. So if time permits, I will just also talk on that one. So the basic idea of principle of neural networking has appeared in many fields, in artificial intelligence, cluster analysis, belief functions, machine learning, data mining, database, and many more. Let me not confuse with the terms. So these are all concept-wise. That practical part I'll just come across just after this. So the two terms normally we come across. One is the level, at what level we are providing information, and what is the component, what is the granular concept. Okay. So in philosophy, in human knowledge, what we do in human knowledge also organized in a multiple level of hierarchy that you have already realized. Okay, the low level, basic level consists of direct perceivable concept, and the higher level is more abstract concept. That is similar, I think, the example what I gave in the paper writing. So the most high level one is the title one. So title one is the most compressed version of the paper. So what is the next compressed version of the paper? That is abstract. So that is what the meaning here is, that higher level informations are mostly abstracted form, compressed form, approximated form. Okay, and low level informations are more clear informations. So like that, this granularity normally we come across. And as a human being, we understand the real problem better way, and we can provide the solution at different level of abstraction that we do in our decision making process. We may not realize that one, what kind of different level of abstraction we follow while taking a decisions, but we do that level of abstractions. Okay, and human can focus on the right level of granularity and change the granularity very easily. But the question is not that how we take the decision. The question is how a machine is going to take a decision, keeping this point in view, keeping this granularity concept or incorporating the granularity concept in the machine, so that machine learning, pattern recognition, all the things can be a kind of better decision tools for our particular task. Okay, so the task is, can we compute this? Okay. So I'm just keeping. So in set theory, granule may be a subset of universal set, rough set, fuzzy sets like this. In a planning, a granule may be a sub-planning. I hope you are understanding the term granule now. Granule means a component of informations which we get from the large component. Okay. So in theorem proving, a granule may be a sub-theorem, right? Okay. So there are two things normally plays a very important role in granular computing. One is shape and size. So what does it mean is that when the information is in a higher level, we call it a large shape and size. Large shape means information is in a broader sense. So that in that sense, we are talking about shape and size. Okay. When the information comes to the lower level, we call it shape and size is the smallest one. Okay, it's something like that in a paper writing. So the abstract title is having a broader sense, but when you come to the lower level information like text, it comes to the lowest size and shape. Okay, so in terms of information also we use the term shape and size. Okay, whether our granule size, shape are under our control or not, because the shape of the granule actually help us to make proper decisions or not. Let's say, for example, I'm showing you the one figure here, one leaves, some 7 leaves are there here. You just try to understand. So 7 leaves are there. So if the moment I show you this figure and I'm asking you, tell me what is this, you can easily say that these are the figures of a branch of the tree and it contains 7 leaves. But let us say if I am showing this information, this greenery part only, and I'm asking you, tell me what is this? Can you tell? It's impossible. So what do you expect actually? You expect to increase the information's level. Okay, so just by making informations more low level. Okay, so like that, it will increase the information from its shape and size. Your visibility, your understanding level about the informations will increase. It is something like that. Let us say in a paper, when you see the title of the paper, you may not get the complete information about the paper because it's a compressed version. So to know about more about the paper, you may read the abstract. Okay. So still, if you are not convinced, then you may read to the text level. So likewise, you increase the information's level. Okay, and accordingly you take the decisions. So that is what the meaning of shape and size. Then I'll come to this little bit mechanics part of that one, so that will be much more clear to you. What is the meaning of shape and size of the granules? It is the granular size, you can say. Let us say size, if you want to understand in the physical point of view, granule, a component or a information, which is a small information or big information, like that you can try to understand. Okay. So in set theory, let's say, let me give you an example. In set theory setting, the cardinality may be used as the size of granules. Okay. So this is how a shape and size of the granule normally can be understood. And you might have realized by this time is that if the information is very high level, that is also a problem. And if the information is in the smallest level, that is also a problem. It is something like, if noise is more, it's a problem to take a decision. If the information is very large in terms of contents of the information, then also it's a problem. You are understanding, right? This is what we talk about in the communication theory. Okay. So more information is a problem, less information is a problem. So more information where we get, to the lower level information when we get, then we get a more information. Less information when we get, higher level information we get. Okay. So we need to make a balance. At what point we should reach, and so that we can take a better decision. So that is what the granularity come into the pictures. Okay. So what we do normally is that sometimes the granule size is very small and it is very difficult for us to understand and try to take a decision. So what do we do? We merge one granule with other. That means we merge one sort of information with other information. So information merging we do. So one can combine many granules into one. Likewise, one can decompose a big granule into small one. So both the way you can do. So information merging, information breaking. It all depends on at what level you want to take a decisions. So this is how we normally do in information granulations. And the advantage here is that this leads to the clarity and simplicity, because it doesn't lead to a complex situations. Wherever we want, we can stop and we can take a decisions. It is based on requirement wise. Whatever it is required, you provide that. Initially, I gave examples, right? When I am asking what is the weather condition, you should provide me something like it's a cloudy. You should not provide me the decision like what is the temperature, because going to the temperature level decisions, you are spending much of your effort. You are using more efforts. But when your problem is not asking you that level, why you are providing the answers? So that is the main concept here. Whatever level requirement is there, at that level only you take the decisions, and things will be much more easier and simple. That is what the concept of granular computing here. Anyway, so I'm just skipping this part. So there are two level of computations normally we do. One is the granulations and computing reasoning with the granules. That we'll understand a little bit more when we go to the practical things. So I'm just skipping this one. So if you want, I can share these slides. Okay. Okay, I'm closing this one and opening one more slide. My new slide is visible now.
Yes, sir.
Okay, okay, okay. So as I told, it has application in many fields or domain. You can see what kind of incorporation I can do with granular computations. Okay, so granular concept is incorporated in fuzzy set theory, rough set theory, wavelet theory, neural network. So accordingly, your model and concept will change. Wavelet granulations, neural granulations, rough granulations, fuzzy granulations, like that. Further, you can combine these two granular also, like rough and wavelet, rough and neural. See, these hybridizations you can play with that one, because you can understand what is the advantage and requirement of hybridizations. Okay, so because why we do that, because we are not getting a specific answer, specific solutions from a particular solution, particular tools. So what we are doing is that, because everything has some has its own advantage and disadvantage. So what we do, we take two models and extract the goodness of this model and we merge them. So we call it the hybridizations. Okay, so like that also you can play and you can get a better decision, because our final goal is to get a better decisions. Sometimes we don't bother about the complexity. Now the granular space also you can have. If you are working in the time domain, you can say that my granular is in time space, time domain. If you are working in frequency domain, you can say that my granular space is frequency, time frequency domain, neural space, wavelet domain. Okay, so accordingly you can formulate your granules. Means you can formulate your informations in what format you want to see your information, so that it will be easier for you to take a decisions. The main driving force, as I mentioned here, is the fuzzy set theory and rough set theory. Okay, and its applicability to wavelet transform, neural network, so many things are there. Okay. So I'll not go to that particular fuzzy set and theory, rough set. I hope it is understood to all of you. I'm asking, should I go into little bit of fuzzy set and rough set, or should I skip this one? Can someone respond to that?
Please go ahead, sir.
No. Should I go along with the fuzzy set or rough set, or should I skip this?
You can go, sir.
Okay. So as I told you, that main driving force of granular computing is fuzzy set and rough set. Just a small concept of fuzzy set and rough set I just wanted to tell, so that things will be much more in a streamlined way. So fuzzy set, we all understand that one. Okay, fuzzy set is not a fuzzy in essence. It's a precise logic of impressions. So most of the time we understand that fuzzy set theory is fuzzy in nature. Okay, it's not fuzzy in nature. Okay, so the point of departure in fuzzy logic is something like that. So you all understand. Now I'm just giving the example of a fuzzy set theory in the granular point of view. Okay, let us say I'm asking, what is the age of this person X? So my question is like this: age of a person. Now age of a person can be anything. In the higher level, what is that age of the person? Either young or old. In the next level information, what is the age of a person? Less young, more young, adult, less old, too old. This is the next level. Now what is the next level of age of a person? You may say year. At this year somebody is born. What is the next level of information? Exact month. Then what is the next level of information? The exact date. So to know about the age of a person, you just try to understand what are the different levels of granularity. These are called granularity. First, higher level granularity is young, old. Next level granularity is less young, more young, less old, more old. The next level of granularity is something like adult, child, kids, too old, less old. Next level is year. Then next level is month, date. So these are the different things. So which level you want to be satisfied, that you should understand. So if you are understanding that one, what questions it is asked, what should be the answer for that questions, then stop your analysis there itself and provide the decisions. That is what the meaning of granularity and granular concept. So fuzzy set is the one of the best approach which we can utilize the granular concept, because the granular concept has come from fuzzy set theory. Okay, because this granularity is there. So I'm just assuming that you have a little bit knowledge of this fuzzy set theory. So this is what the fuzzy set theory in the granular concept is something like that. It breaks the informations in the possible level of granularity. Like this age of a person, I broke this information age into like this: young, old, not less than, less than. So this. So to break this information, fuzzy set theory can help me. So you can take a different membership function to break that information age into young, old, less young, old, young, adult, child, old, or year of the birth, month of the birth, date of the birth. So all the things you can do using fuzzy set theory. That's why the fuzzy set theory is actually the creator of the granular concept. So what advantage we are getting? Because as per the requirement, we can provide the information. That is what the advantage is, and that's not a small advantage. So we can get a better, I mean, relatively better advantage than the any other kind of analysis. Okay. So like that, there is one more concept. See, this is what I was telling. Okay. So age in the x-axis, you can see age. So it is the higher level information. So we can break your informations like this. Okay. So to break this information, we can use fuzzy set theory. So that's why fuzzy set theory helps us to granulate the informations to the possible extent. Okay. Now let me give you one example, live examples how fuzzy set theory is practically we appreciate. Okay. So let us say one you are seeing this right side, one image is there. Okay, one small water bodies and some ground level and a sky is there. Let us say I'm asking in the concept in the context of image processing, you just segment that image. You just cluster the image. Okay. So there are two kind of clusters broadly. One can be crisp cluster, one can be fuzzy clusters. Okay. I'm just giving you a some kind of feel. What is the advantage of fuzzies? So if you want to cluster this image, you can cluster this image in a crisp way like this. One blue region, the these water bodies, and green region, and the sky, something like this. But if I partition this image like this, probably I may not like that. So what should be the proper partitions? Proper partitions will be a kind of clusters which can easily distinguish between one land cover to another land covers. So that kind of concept is actually fuzzy concept. Okay. So we can incorporate granular computations, granular concept here also. So that the moment we can incorporate granular concept there, then our granular shape and size will be either crisp or fuzzy. Okay. So that's why we call it a crisp information granulation or fuzzy information granulation. So I'll talk more about the fuzzy information granulation. So that means my breaking of information is fuzzy in nature. Okay. So I'm just giving one data set, some example data sets. Just you see the data sets. This is a scatter plot of a data sets. In a decision making process, we always come across like this. So there are 6 classes are available. Okay, 1, 2, 3, 4, 5, 6 classes. So it's actually vowel data. Okay, vowel means we have 5 vowel data and 1 characters. Fine. So all these vowel data were collected to form a database, and these 6 classes of data are available. If I make a scatter plot, it looks like this. Now you can understand how one class is overlapping with other class. So this is what a real-time scenarios. In most of our real-time problem, we face a lot of problem to take a decision because of this problem. What is the problem? Overlapping regions. One class is overlapping with other class with maximum regions. So we are unable to understand. Let us say, for example, this one. This is one. Sorry. Okay. Let us say at this region, I am having a sample here. Now just try to understand. This sample belongs to this class, this or this class. It is very difficult. So these are the real-time scenario where we human being also faces problem. So that's why we take the help of fuzzy set theory and try to provide better decisions. Okay. Broadly, we can categorize the granulations of the informations in a fuzzy way into two types. One is class dependent, another one is class independent. What I mean to say is that how many classes are there? There are 6 classes are there. If you want to break the informations with respect to the classes, then I call it as a class dependent fuzzy granulations. If I break the information without taking considerations of the class level, then we call it as a class independent. So it's something happens like this. Just see these images. This is what actually a scatter plot, F1 and F2. There are 4 classes data are there. So these 4 classes of decision making, whatever just now I am telling, this is a pattern recognition point of view, and this can be applicable to any problems like remote sensing, data analysis, anything. Okay, that I'll come to that point. So there are 4 classes are there, and each of the classes contains some level of information about that particular class. Okay. Now the task is whether you are breaking the informations with respect to class or without considering the classes. So if you are breaking the information with respect to class, we call it a class dependent relations. If it is not with respect to the class, then it is a class independent relations. Just see this graph figure. So this symbol actually they are called the membership function of the fuzzy set theory, which is actually helping us to break the information, to granulate the information. Now see, let's talk about the class 4, C4. In class dependent granulations, the function is actually covering the whole class. Likewise, in C3, the function is covering the whole class, C2 and C1 also. But in class independent, you just see it is not covering the whole class. That means with this breaking of information or the analysis of information is independent of the class information. So this is called class independent relation, and this is called class dependent relations. Okay. So these are nothing but a membership function. Normally we use a fuzzy set theory. Okay. So if we want to see the break of informations like this in a different granular formations, it looks like this. Okay. So in the x-axis and y-axis, the information contains. So I could break the information into the 16 components. So each of the region is one component of information. So I believe you are understanding, right? So each of the number, whatever number I have put here, each of the component is representing one sort of information. If I combine whole thing, that is the high level information. So if I am breaking them into 16 components, each component is a low level information. You just try to understand that information breaking in this way. Okay. So because fuzzy set theory helps me to do that one, so that is why this whole concept is called fuzzy information granulations. Now see, I believe you are understanding here, x-axis is actually the F1 feature, y-axis is actually the F2 feature. Okay. Now, when I'm breaking the informations, either class dependent or class independent, actually I am breaking the feature space. Okay, because where my information resides, within the features of a pattern. Okay, so if I break that information, what does it mean? I am breaking that features. See, I'm using the word actually break. I should not have used that word break. Break doesn't mean that you are chopping the information. Are you getting my point? You are just partitioning that information in such a way that each partition will act as a granule for you. Okay. So let us say I have a pattern of n number of features. Okay, F1 to Fn. Now, if I want to break the information with class independent case, then the way I did here, one membership function this one, another one this one, another one this one. So there is a name we have used. One is called low, medium, and high. Okay, so that is why this low, medium, and high. That means each feature informations will be partitioned into 3 sub features: low, medium, and high. For example, let us say I am breaking these informations, that age informations. Okay, I'm breaking the age informations into 3 components. So age can be broken with low, medium, and high. How? One is I can say adult, another one is the young, another one is the old. So these 3 components are actually the breaking version of the original information age. Okay, that is how a information is partitions here. But in class dependent case, it is actually taking care of the class informations, and that is why these informations are broken like this. Now, what is the advantage in doing like that? You might have realized that one, but here in mathematics also you can really see a single feature is represented by 3 features here in class independent case, and here a single feature is represented by number of classes present in that. Originally I had 1 features. Now that same feature is represented by 3 features. You may call them as a sub features, but they are the 3 components of the original features. So is it not the partitioning of the information? Is it not the breaking of the information? It is actually the breaking of the information. And what are we doing that? To understand the feature information in a proper way. So that is what the information granulation is all about. Okay. Anyway, so I'm just keeping this rough set part because it will take much more time, and I'm just coming to the some practical applications here. So I'm skipping this rough set thing, but this is one way of information granulation. I already discussed about the fuzzy set theory based information granulation. This is rough set theory based information granulation, which is another way like fuzzy set. So let us not discuss at this point of time because time is not there. So I'm just skipping this one, and also I'm skipping this part. Okay, now I'm coming with a classification model. So I believe you are having some idea about the information granulations and how that information granulation concept is used for taking decisions using a classification model that we will discuss here. So this is a simple classification model that we all know. Okay. So this is the input pattern. That input pattern will go to another step where we normally granulate the informations. That is why we have written generate granulated feature space. So this is original feature space, and this is called granulated feature space. Okay. Now this granulated feature space goes to another level of analysis that is called removing the redundant informations. Okay. Once we remove the redundant informations, this granulated feature space number will reduce, and those reduced informations will go to here in another component where we can develop a pattern classification model and provide the class levels. I hope you are understanding this cycle of decision making process. Okay. I skipped this rough set theory because here rough set theory is used to remove the redundant informations obtained from the granulated feature space. Now let me discuss a little bit why this situation comes to remove the redundant informations. Because given the informations, we will never realize what should be the proper granularity of that information. That means to what extent we can break that information. From the beginning, we never know that one. Only we know that this big information is not understandable to me, and that is why I need to break them. But I don't know to what extent I should break. Okay, so this is something like that. Let me put in another scenario. Let us say you are giving a problem to me to solve. Okay. Now, after looking at the problem, if I cannot understand that problem, I cannot provide the solution. Okay. So assume that I didn't understand the problem. So simply I will say this problem is very big for me. Don't you say that? This problem is a very big problem for me. Why it is a big problem for you? Because I am unable to understand that problem. Why you are not able to understand the problem? Because information within the problem is not under my control. I am unable to comprehend. I am unable to analyze the problem because I am not able to understand that problem. So you may suggest me, you do one thing, you break the problem into sub-problems. You break the problems into sub-problems. What does it mean? That means you break the information into sub-informations. Probably you may be in a position to understand the problem in a better way now. If you are still not able to understand the problem, break the information to the next level. So you will keep on doing all the things till you can understand the problem in a better way. So there is a saying, you know, divide and conquer rule. We all realize that we all understand that these British people ruled us with the same concept, right? Divide and conquer. They divided us based on our community mentality, psychology, and they ruled us. This granular concept is actually based on that one. Divide and conquer. If that problem is not understandable to you, break them into sub problems. If you are not understanding, break them to the further level. So this is what the concept of granulations, and which we can use here to take a decisions. So when you are giving the input pattern in the form of features, that is not understanding to me. So what I did, I broke them using the granular information. So that becomes granulated feature space now. Okay. From the beginning, I will never realize what should be the breaking point. At what point I should stop. I don't know, because it's a very difficult task to understand that at what is the granularity of my information breaking. So what I did here is that I just tried to avoid that step. So what I did, I broke that information to the possible extent from the beginning itself. I broke the information to the possible extent from the beginning itself, to the smallest component. Okay, because I don't want to scratch my head to understand the level of granularity. Okay, so I broke them into possible extent. Now it is very clear that if I'm breaking the problem into sub-problem to the possible extent, probably the smallest problem component, smallest information component may be a redundant one to take my decision. I believe you are understanding the term redundant term here. The information which is not useful to me is redundant for me. Okay. So the moment I'm breaking this feature information to the possible extent, there is every possibility is that there is introduction of noise, there is introduction of redundancy, there is introduction of vagueness, there is introduction of uncertainty. So all these terms will be there within the feature space, within the information space. So another problem came into me. Initially, my problem was I was unable to understand. Now the problem is I have so much of information that I am unable to decide which one is correct and which one is not correct. So for that reason, I am using here a feature reduction techniques, that is called fuzzy Ropset theory, which is also a granular computing scenarios. And using that, I am reducing the feature space. So what actually I am doing here, I am removing the redundant component and I am choosing those smallest component which is actually informative to me, which are actually going to contribute towards my decisions. And that is what I am doing here in this second step. And after doing that, I am just simply developing a classification model and finding out the class name. Okay. So I'm just coming to an example. I'm just keeping this on. These are different. Just 1 second. I'm skipping this. Okay. So here is a classification model based on fuzzy granulations. Then the classification model is applied to land cover classification, land cover region classification in remote sensing. So based on the granulated informations, we have developed 5 different models: F1, F2, F3, F4, and F5. Okay. As I told you, just recollect that this one, this classification model, my contribution is in the first and second component, not in the third component. I mean to say that third component is actually a classifier, a classification model. So I'm not touching anything, or I'm not contributing anything to the classification model. What I'm doing here is that I'm pre-processing the information in such a way that my classification will work better than the previous scenarios. Okay. Instead of performing the second and third step, I can directly give my input pattern here to the classifier. Are you getting my point? I can skip these two steps and I can directly put my input pattern here to the classifier without pre-processing. Why I did pre-processing? Just to make the decision perfect. That is what my intention is. Professor Ramarao, just 10-15 minutes. Another 10-15 minutes I require. Am I allowed?
Go ahead.
Okay. If you don't allow also, I don't listen to you.
You are my boss.
Okay. So I developed 5 models here: F1, F2, F3, F4, and F5. Okay. Just see what is the specification of this model 1. Model 1 is the k nearest, simple k nearest neighborhood algorithm, neighborhood classifier. Okay. So we are not trying to understand that one because that is a very simple classification model. That model we are using here, and we are trying to understand that how this granulation concept actually enhancing the performance of k nearest neighborhood classification. You can use any classification model instead of k nearest neighborhood. You can use a neural network. You can use a some Bayesian classifier. You can use some other classification model, and you can see the advantage of the granulations. Okay. So you just see F1 is the KNN classifier, F2 is the CI fuzzy granulations plus KNN classifier. Meaning here is that CI means class independent fuzzy granulation plus KNN classifier. Okay. Third one is the class dependent fuzzy granulation and KNN. So this part, this classification part, actually we are not talking about. We are only talking about the pre-processing part using the granulation concept. Okay. F4 is class dependent fuzzy granulation and PARS. It is a offset theory based FHS selection, and then again KNN classifier. So the difference between the 3 and 4 model is that in model 3 we just broke the information using class dependent, but we didn't remove the redundant feature. But in model 4 we broke the information and also we removed the redundant information. And model 5 is the best one among these 5. What it did? It granulated the information using class dependent fuzzy granulations and remove the redundant features using one NRS. It's a kind of offset based feature selections, and again the KNN classifier. Okay, let's try to understand this 5 model performance here. Actually, it is applied to this remote sensing data. These are the remote sensing data which we have used. So on that, we have applied that. I'll show you the land over classified regions also. Just see this performance analysis. With 20% training set, with 50% training set, x-axis is the model and y-axis is the performance accuracy. In this figure, this is x-axis is the model and y-axis is the kappa coefficient, and here is the computational time. Okay, and this simulations are done in MATLAB environment, and you can easily see the performance of all these 5 models. The model 5 is performing better than the rest of the model. Okay, so your performance increment is happening from model 1 to model 5. All the models are using KNN classifier. Please remember that all the models are using K nearest neighborhood classifier, but only difference is that how you are processing that input information. That is only varying here. Model 1 is simply KNN, model 2 is the class independent, model 3 is the class dependent, model 4 is the class dependent plus redundant feature extraction, and model 5 is the class dependent and another feature redundant redundant feature extraction. Okay, so you can see here also, and you can see here also. You can easily understand that because you are doing some pre-processing, obviously there will be a little bit more computations. So computational time will be a little bit higher in these cases, but it is not much more that we cannot deal with that one. Okay, with that computation time, we can compromise and we can get a better result, because here our target is to get a better accuracy, not the talking about the computational complexity. Even if it is there, computational complexity is not bothering much for us now. Now, as I was telling you, right, instead of k-nearest neighborhood classifier, you can use some other classifier also and use the same pre-processing things and see the results. So see, these 5 things are 5 model for KNN, k-3, k-5. Here MLP, neural network. Here maximum likelihood function. So whatever classification model you can think of, you can use that, and you can see the advantage of the information granulation. Okay, so your performance of the model is further enhanced just by pre-processing stage. Okay, this is another one, and this is one remote sensing. Okay, sorry, that image what I showed, that was a different image. So we have applied on this image IRS-1A data and spot data. These are 2 remote sensing data, and what we have done is that we have considered 6 land cover classes, and these 6 land cover classes we have formulated one database, and we have taken some samples training and testing, and the performance of the model is analyzed. Okay, yeah, these are the 2 land cover regions of the 2 different images, image 1 and image 2. This is IRS-1A and this is spot image, and this is what the classified image. Just see the original image, this is the classified image. Okay, so the classified image, first image is using model 1, and second image is using model 5. So there is, you can easily see that qualitatively that model 5 is performing better than model 1. So we have also quantified that one. If I zoom that region, small region, also you can see that model 5 is segregating the information in a better way than model 1. So so this is another way of performing the analysis. What it is done is that the clustering indexes we have also used beta and db, just to see that whether our segmentation, whatever we have got the result here, whether they have done properly or not. So we have used beta and db index, and in terms of beta and db index, it is actually the quantification of the classified image. Just now I showed this one. Okay, so in terms of these 2 terms also, we can see that model 5 is performing better. So to interpret this result here, you'll see more is the beta value, better is the accuracy. So the first result, it is actually based on training sample. So obviously this beta value will be very high. Okay, and model 1, model 2, model 3, model 4, and model 5. So model 5 is giving better result than all of the model. Let me again tell you, all models are using the same classification model, but their processing procedures of the input information are different only. Okay. Similarly, here in DB, less value of DB is better accuracy. Okay. So model 5 is the smallest value compared to others. So for the other remote sensing image also, this is similar kind of results also we got, and this is the beta and db index result obtained from the land cover classes. Computation time, if you want to measure, yes, it is true that model 5 is taking much more computation than model 1. So we can see, but it's not too much. It is taking 322 seconds, and this is taking 350. So only difference of 25 seconds. I don't think that 25 seconds is a bothering term for us. So we can use that, and we can get the better advantage. And the conclusion is something like that. The advantage of the offset theory based and fuzzy set theory based data accumulations we could realize here, and we could model 5 different way using the same classification model. As I told you, instead of KNN, you can use any other classification model, and you can see these advantages. And finally, we realized that class dependent fuzzy granulations along with the redundant feature selections is performing superior, and the cost of computation time is not much, and which is not a bothering term. And with this, I will conclude my talk. And if there is any queries and things, please let me know.
Thank you, sir. Sir, now we will have a question answer session. Participant, kindly unmute and ask the question.
Anything is there in the chat box?
Sir, there is one question from Ashish Paul. Sri Ashish Paul, you can ask the question.
Good morning, sir.
Good morning. Please tell.
Sir, my question is, as you were talking about your expert in remote sensing, I wanted to know, can I use this granular computing for habitat modeling of an endangered plant species?
Is it a decision-making problem?
Yeah, it's a decision-making problem.
I'm sorry, my background is not from remote sensing. That's why I didn't understand your problem.
Okay,
So
I will help define. I'll help to localize. Ashish Paul, the question is that what is actually the modeling you like to habitat modeling? Do you mean that the mapping of the habitat over a period of time?
Yeah, mapping of this particular species for the conservation purposes.
Yeah, that is right. A habitat of a particular species over a period of time. That's what you mean. Habitat modeling, right?
Yeah.
So that can be done, for example, over a temporal mapping and change detection studies, which is very well, as you can see, the granular computing also a sort of technique where you can actually produce kind of classification maps. So obviously, it is a case.
Yeah, whatever the problem is, if that problem is requiring a classification model, then you can use this granular concept. I'm sorry, because I don't have the background of remote sensing. I cannot understand your remote sensing problem. So if you are using a classification model for your task, yes, this concept can be useful there.
Yeah. Okay. Thank you, sir.
Obviously, finally, it will be degenerated with a problem of classification or pattern prediction. So it can be a tool.
Yes. Thank you, sir. Thank you.
So the moment you want to take a decision, this will be helpful.
Yes, sir. Yes. Okay. Thank you, sir.
Okay. Thank you.
Any other questions from the participant? Yes, Dr. K. Venkatesh Rao, sir, please ask.
Good morning, sir.
Hello.
Good morning, sir.
Good morning, sir. Please tell, sir.
Sir, how can we use this granular computing in online analytical processing, OLAP?
It must be having feature space, right? In your task, whatever you are asking,
yes.
It is in the formation of a pattern and features, right? And
yeah, I tell something. For example, we have this online analytical processing uses a data cube.
Okay.
Let us assume we have our country,
okay,
states,
okay,
districts, then the taluk or mandals, villages, and within villages we have land parcels.
Okay.
This is one hierarchy.
Right.
Then we have another hierarchy. We have soil. The soil itself will have a characteristics like what is type of soil structure, texture, and all.
Yes.
Then we also have, that is another dimension.
Right.
And we have another dimension like a water resources availability for that particular.
Yes. Your voice is not audible. Oh yeah, please tell.
Yeah. Another dimension is timeline.
Right.
Another is other conditions.
True.
Now we have a citizens.
Okay.
We can have a hierarchy, something like
Okay.
These are the multiple dimensions, and each dimension may have a hierarchy.
Right.
Now, I just want to classify.
Okay.
I can generate different classes at different levels. Say citizens. Classify the citizens into rich, poor, middle, above middle, and all. Based on they are associated with the land parcels, and land parcels are associated with something weather conditions, time, and water resources.
Okay.
And I also can classify the villages which have a good resources. They are, we can say, rich villages.
Yes.
Similarly, at district level, taluk level.
Okay.
So we can also generate, because time also I have a dimension.
Yes.
draft conditions at some particular point
Yes.
of time, which dictates which one.
Yes, yes.
So this kind of this is basically a data cube containing multiple dimensions.
Understood.
Each dimension is associated with a hierarchy.
Okay.
And we want to model this, and maybe if data available, we can generate.
Yes, yes.
Physics
Now I'm understanding your problem. Yes, it is rightly applicable to your task. Whether you take the decision based on the rich, poor, all the things, based on the soil, based on the different whatever dimensions you are talking about, your hierarchy is within your control. So this hierarchy and their hierarchy is different actually. This is going to make a hierarchy within your hierarchy. And once you can do that one, you can make a decisions. I believe any classification model can be useful for your model, for your task. Any classification model can be useful for your task, right? Now, if that is the case, yes, this is a component of this classification model. And it is rightly applicable to your particular domain. Whatever cube you are talking about in different dimensions and other things, you can directly use it. I mean, there is no, confusion in that one. It's directly applicable. It's directly applicable.
Okay, thank you.
Thank you. Thank you.
Any other questions? Participants?
And if there are no questions, fine, then we end up. Anyone finally?
Sir,
Excuse me, sir.
Yeah, please.
Okay, sir.
Yeah, please go ahead.
Please continue.
Actually, as you mentioned that for the case of remote sensing image, so that suppose for the before doing the k nearest neighborhood classifications, so we normally directly use the remote sensing image and carry out the k nearest neighborhood classification. Right. So where our pixel intensity value only our features or informations.
Correct.
So for your granular technique, in between you are measuring some sub features from the remote sensing image, and that sub feature you are using in your through granular you are doing sub feature, then you are
developing the model.
Okay. So now question is that you are the sub feature you are measuring through the granular. So that technique you are taking the fuzzy set, or fuzzy set you are using for the merging the some of the redundant features. So there maybe my understanding may be a little bit this thing.
No. Let me just put the things in again. Original information is there, right? Whether it's a spectral information or spatial information of your remote sensing images, whatever it is. Okay, your original information is there. Okay, let us say we are talking about a multispectral image. Okay, we have 4 bands of information, and each band contain one information about a particular spectral things. Okay, now we are using here fuzzy set theory to granulate each of the band separately. We are not combining those 4 band of informations and building the model. We are taking each of the band, and that band is further analyzed, further decomposed into several components. And once that is decomposed, let us say we are using class independent fuzzy granulations. So class independent fuzzy granulations, what it does, it decomposes the information into 3 components: low, medium, and high. Okay, so originally I had 4 band of information. Now each band is further decomposed into 3 component. So now my band structure will be, instead of 4, now it will become 12. So my 12 component based fuzzy feature informations will be the input to your model. Originally 4 was there, now it became 12. That is the only difference.
Sir, here just I wanted to mention that is whether in that case, whether we are giving some training data, means is it a supervised classification technique or?
Classification model part we are not at all touching.
Okay.
Whatever the way you are using your
Okay.
classification model, the same things we will use. Training, testing, supervise, everything is same.
Okay.
Only thing is that instead of giving original features, we are giving granulated features. That's the only thing. Only at the input level we are processing. Rest of the things are same.
Okay.
Originally I had 4 features. Now I could get 12 features. So instead of 4 features, my pattern will contain 12 features, and based on that I will take the decisions.
So last just question. So in that case, what is the difference between that convolution neural network also we are convolutions you are carrying out and carrying out the features? So what way difference the convolution, through convolution we are measuring features, and through granulation technique also we are measuring features. So whether we can compare whether is there any difference?
See, if I understand your problem, you want to incorporate the granular concept in the convolutional neural network. Am I right?
Oh, okay.
No. Are you trying to incorporate the granular concept in convolutional neural network?
No, sir. Actually, I am convolutions. That convolution we are doing, convolution through convolution we are reduction the features, or abstract level we are measuring, like pooling, convolution, max pooling or mean pooling we are doing. So that way also we are feature we are measuring.
No. This is actually different one. See, in CNN you are giving the original image. Okay.
Yes.
You are giving the original image, and from that image, using the different convolution layer, pooling layer, your ReLU, and so many things are there. You are extracting the features.
Okay.
That part we are not at all talking. That part we are not at all talking.
Okay.
Now, when you are giving original image to your CNN, don't give that original image to CNN.
Okay.
To decompose that image into sub images using the convolution component, and those decomposed image becomes the input to your CNN.
Okay.
So, for example, let us say you are giving 4-band multispectral image to your CNN. So it contains 4 band.
Okay, sir. Yes, sir. Yes.
Okay. Now you decompose each of the band into 3 component. So that means each band becomes 3 band. So 4 bands becomes 12 bands.
Yes.
Now instead of 4 band, your input to the CNN will be 12 band. So the depth part, that spectral part, that feature vector will have more component now. Now your CNN will not face any problem whether you have.
That is true. That is true.
So then you run your CNN after that. So you will see that your performance will just increase. Originally using 4 band, whatever result you are getting, now using 12 bands, obviously there is a possibility that your performance of CNN will increase. That is what the purpose of this granular computations.
Thank you very much, sir.
Sir, can I ask a question? I'm Dr. Jyoti Rupa.
Please.
Sir, you are speaking about granular computing. Can I know that in India there are so many smart city concepts going on from the central government? So is this concept used for smart city concept?
But first of all, I need to understand whether whatever you want to do, whether it requires a classification model or not.
Pardon me, sir?
Whatever task you are talking about, first let me know whether it requires a classification model or not to take a decision.
If the answer is yes, like
if the answer is yes, it is directly applicable there.
But I'm asking, like, practically are they doing it, sir? Like the central government.
I have applied to the remote sensing data. I have applied to the medical image data. I have applied to the telecom data. I have applied to even to this recent COVID liver images and analysis. So that also. So because I am not touching the modeling part, what I am doing is that before modeling, whatever input it was going earlier, now that input I am changing. So my input component is only changed. So rest of the processing are same.
Okay, sir. Thank you.
The next question is from Sudhanshu. Sudhanshu, kindly ask a question. Okay, then I will read it out for you.
Yeah,
if original image has high dimensionality, then can the further expansion of the features can lead to excessive loaded computing resource?
Yes, yeah. What you are telling is that is true. If original feature space is very high, for example, let us say hyperspectral images. Okay, so your hyperspectral image contains 100 bands or 200 bands. Okay, now instead of playing with 200 bands, now you are going to play with 600 bands. So computational complexity will be little bit more. If you want to compromise with that, and if you are stick to your performance, obviously my answer will be you can use that granulations to your task. Yes, computational complexity will be a little bit more here. So what we can, what is the suggestion here is that let's say you are working in hyperspectral image which contains 200 bands of images. Okay. Now it is obvious that 200 band of images will not be informative at all. Some of them will be redundant for your task. So before processing or before making it granulated, before granulating this 200 band, you use a PCA, for example, simple PCA you use on that one, and just reduce that band of information to 50 or 40 or 60. So your 200 band becomes now 50 bands. Now you granulate that 50 bands and build the model. So that is what my suggestion is. Or otherwise, directly you process that 200 band into 600 band, and then you again remove the redundant band out of the 600 band. So you will have to compromise with the complexity part here because you are doing some extra computation just by pre-processing your data. Okay. So actually you are not bothering about the computation, you are bothering about the performance. So if you are bothering about the computations, then you need to tactfully act on that. Before processing, you remove the redundant part, then you granulate. If you have decided to use the granulation things, then from the beginning itself you remove the redundant part. That will originally, I mean, from the beginning it will reduce your feature space, and then you use your granulated information, and finally you can end up with a good result.
Thank you, sir. Next is from Sri Subhoshri.
Yeah.
Subhoshri. Sir, his question is for canopy height measurements, can granular computing be helpful?
Can you read it again, please?
For canopy height measurements, granular computing will be helpful.
What is that canopy height measurement? I don't know.
Canopy height, sir. Height.
Can you explain that problem a little bit?
Okay. Sir, she meant to say that for measuring the canopy height of various trees, how this granular computing is useful. Maybe that is.
I don't understand, and that problem is not understood to me. But one thing I can tell, if your task is requiring a classification model to take a decision, then you can directly utilize this one to your task, your model. I'm sorry, I didn't understand your problem, but I can only assure you that if your task is requiring a classification model to take a decision, yes, this can be directly applicable there.
Okay, thank you.